So today's lecture will be about applications of the sorts of ideas that you learned about in the first two homework problems. This material that we went over last time, where you have a differential equation with some parameters in it, and you can look at all the different, qualitatively different kinds of behaviors you can get for different choices of the parameters. So the lecture is basically going to be about the other three homework problems, 3, 4, and 5. Those will be the applications that I'll have you explore. And maybe I'll discuss 3 in depth and then just put a few comments for the other ones. So 3 is this example that I'm stealing from your textbook, and it's a really fun one to think about. So let's start kind of simple, and let's just say let x be the amount of glucose in your blood. Okay, so I'm not giving any units because it's actually not important. We're going to have parameters, and the parameters have whatever units they need to have in the end. But the point is it's an amount. So it could be a mass, or the literal number of glucose molecules, or it could be actually a concentration, which would not be an amount, but effectively you end up with the same thing, since we're not going to talk about changing the volume of your blood throughout. So if we make x a concentration of glucose, that's fine too. It would just be a scalar multiple of the amount of glucose. Okay, so start here. Now let's say that there's some equilibrium level of glucose in your blood that your body wants to have. And if there is excess glucose, then it'll just kind of go away over time and decay, naturally decay towards the equilibrium. And if there's a deficiency of glucose, then your body maybe will try to, well, I don't know what it'll do, but it'll do something so that you end up with your amount of glucose increasing towards what it needs to be. So to represent these this natural background decay of glucose towards what it needs to be, let's do this. So let's say x prime equals negative gx. So here g is some constant, some non-negative constant. So this is like an exponential decay kind of differential equation, right? Except, okay, if I set it up like this, then I'm saying that x decays towards 0, right? If I set it up like this, x decays towards 0. So any glucose you have just decays over time, and if you just let time run forever, in the long run you go towards 0 glucose. That doesn't really make sense. There's some equilibrium amount of glucose that you're supposed to have, and if you have excess, then you poop that out or whatever. That's the decay. That's what this mechanism is. So you really should put here x minus maybe x naught, or whatever you want to call it, like the equilibrium level. Maybe rather than x naught, let me call it x equilibrium. So this would be sort of x decaying towards equilibrium. If x is larger than x equilibrium, then x decreases, and it decreases proportionally at a rate proportional to how much larger x is than x equilibrium. Okay, well, there's a way we can make this simpler. So right now, if we look at this as this is a linear differential equation, right? But if you write down the sort of linear operator on the right-hand side, ddt plus g is being applied to x, and that equals gx equilibrium, which is some constant. If you write it like this, you see it's non-homogeneous, right? And that's not so fun, since eventually we're going to write down a system of differential equations, because I want to bring in glucose and insulin. And we've been discussing how to deal with homogeneous ones this whole time. If I have non-homogeneous, well, I can turn it into a homogeneous one by shifting, by doing some kind of translation. You've seen that before, but probably easier to just redefine x itself and say, instead of x being the amount of glucose in your blood, it'll be the amount of excess glucose in your blood above the equilibrium level. So let me just say amount of excess glucose in your blood. So the new x is actually what I was calling x minus x equilibrium. So now I can just put x here, and then this is the derivative of the old x minus x equilibrium, which is just the derivative of the old x. All right, so when I do it like this, now x decaying towards 0, which is what this differential equation will lead to, x decaying towards 0 makes sense. It's whatever your level of excess glucose, if the more it is, the more quickly it decays towards 0. Having 0 excess glucose doesn't mean you have 0 glucose in your blood. It means you have the equilibrium level, the like balanced level of glucose in your blood. And negative x now makes sense. It doesn't mean you have a negative amount of glucose. It means you have less than the equilibrium level. So this is our standard trick for turning something into a homogeneous differential equation when the right-hand side is just some constants. All right, now I'm going to define a new variable, which is y. Sorry. And let's say y is the amount of excess insulin in your blood. So that can also have a sort of natural decay to it. So we'll say y prime equals some negative constant times y. So here d is positive. So d is the insulin decay rate. So this is before we put in any mechanism for the interaction between glucose and insulin. So the idea here with decay is that if nothing is triggering the production of insulin or the destruction of insulin, and you just have a certain amount, y, above the usual background amount that you're supposed to have, then that excess amount will just decay. Like you'll pee it out or something. I don't know exactly how it works, but it wouldn't just stay there, right? Your body fluids or whatever are constantly being recycled and stuff. So that's this background decay part. Now let's put in the interesting aspect. And of course this is a simplified model. I don't know to what extent it's accurate, but it's fun to play with. So there's definitely an interaction between these. So there are two mechanisms. So let's say you eat a cookie or something, and suddenly x increases. So let's say you have a bunch of, you have positive x. Suddenly you have excess glucose. Then your body notices that and reacts by producing insulin. And the rate at which it produces insulin, we can imagine, could be proportional to how much excess glucose there is. So I guess I should be pointing here. So y prime, there's a term contributing to y prime, which is proportional to x itself. So something proportional to x, so some constant times x. So here, this is a positive constant. So the bigger x is, the bigger this contributes to y prime. So the assumption here, which is probably a very oversimplified assumption, is that if you double the amount of excess glucose at any given time, then you have doubled the rate of insulin production. So this is contributing to dy dt. And these parameters all have meanings. So like S here would be, if S were large, that would mean that you have a very sensitive pancreas, I guess. Maybe that's why it's called S for sensitivity. A sensitive pancreas, you put in a little bit of glucose and it just reacts by cranking up y prime, producing lots of insulin very quickly. And these other constants also have meanings, like these decay rates. Maybe D means you flush out excess insulin very quickly, things like that. Okay, and there's one obvious missing mechanism here, which is what the insulin does to the glucose levels. The reason your body's releasing the insulin in response to the presence of glucose is because insulin gives your body the signal to take glucose out of the blood somehow and make use of it. There's excess blood, let's start using it. There's excess glucose, let's start using it for stuff. So the more insulin there is, the more quickly glucose will get used or will get pulled out of the bloodstream to be used for other stuff. So here, the rate of decrease of insulin should be proportional to, the rate of decrease of X, of the excess glucose, should be proportional to the amount of Y. So I will put negative constant times Y here. And for the constant, we'll use R. Here we're assuming R is greater than 0. So I guess R represents kind of how sensitive your cells are to the insulin hormone. So if you have a large parameter R here, then I guess that means even just a little bit of insulin will cause you to start pulling the glucose out of your bloodstream very quickly for use for other things. And remember that it makes sense in this model. It's set up so that it makes sense to think about positive and negative X and Y. So like when Y is negative, that means you have less than the equilibrium. Since Y is the amount of excess insulin, the amount above equilibrium, negative Y would be the amount, would just mean that you have lower than the equilibrium level. So then this would cause you to sort of decay up to 0, up to Y equals 0, which is the equilibrium level. And you can see these other mechanisms also sort of saying things about when X or Y are negative. Like, let's say Y is negative, so you have less than usual insulin. Then this term, if Y is negative, then you have positive times negative, and then a minus sign. So overall, this would be positive, which contributes to, so this term would then increase X prime, right? So if you have less insulin than the equilibrium amount, then that makes the amount of glucose in your blood grow more quickly. That should make sense. Okay, so let's summarize. Somehow, let's say you eat a cookie and suddenly that increases the amount of excess glucose in your blood. So X is now large. And X being large makes Y prime large. So over time, Y increases. So let some time pass, then Y becomes, Y grows, and suddenly you have a bunch of insulin in your blood. Excess insulin, more than usual. Then Y's being large, Y's being positive at all, makes this term here decrease X prime. So the level of glucose in your blood decreases faster than the natural decay rate would make it decrease. And then as X gets smaller and smaller, this thing gets smaller and smaller, Y prime gets smaller and smaller. Eventually this term will beat this term, and you'll get Y decreasing due to the natural decay of it rather than increasing. And then one hopes that eventually insulin levels go back to normal. So these two mechanisms here, the mechanism where having more insulin makes the amount of glucose decrease, and the mechanism where having more glucose makes the amount of insulin increase. These are the two mechanisms associated with the two different types of diabetes. So for a normal person, you should have both of these mechanisms working properly, and type 1 and type 2 diabetes correspond to one of these mechanisms being broken. I forget which one is which, but those mechanisms are associated with the type somehow. All right, so let's explore this model in the next video.